Take a look at this incredible vertical landing, which is smooth, sexy, and requires absolutely no catapults or arresting wires. This magnificent machine is the F-35B, a technological marvel that seems to defy the laws of physics with ease. You might wonder why the United States Navy is currently struggling so much with electromagnetic catapults on the Ford. Why do we not simply scrap that complicated system and just decide to use the versatile F-35B instead? It takes off vertically, it is simple to operate, and it is relatively cheap compared to building massive catapults. On the surface, this idea sounds like a stroke of absolute genius that could save billions of dollars instantly. The rest of the world is already doing this, so we should look across the pond at the Royal Navy. They decided to bet their entire future fleet on the capabilities of the F-35B and its vertical landing systems. The HMS Queen Elizabeth is a massive 65,000-ton vessel that operates without any nuclear reactors or catapults. It has no arresting wires, just a simple ski jump ramp at the bow to help launch the jets. This design is simple, it is highly effective, and it proves that you do not need complex steam catapults. You can also look at our own fleet, specifically the USS Tripoli, which is an amphibious assault ship transformed. It has been turned into a lightning carrier, where the F-35B works perfectly without any major technical issues arising. So why does the $13 billion supercarrier, the USS Gerald R. Ford, say no to this easy solution? Why does the most powerful ship on the planet reject the most flexible aircraft currently available on the planet? This is a plane that both the British Navy and the United States Marines absolutely adore for its versatility. The answer to this complex question is not about politics, nor is it about the arrogance of naval commanders. It is actually a matter of cold, hard geometry that dictates the survival of the ship in modern combat. We need to look closely at the internal cross-section of the F-35B to understand the fatal flaw in this logic. To hover in midair, it has to carry a massive lift fan positioned right behind the pilot's cockpit. In the critical eyes of a naval engineer, that lift fan is not a miracle of modern aviation technology. It is actually a void that consumes the space of the two things that determine life and death at sea. Those two critical elements are fuel for long-range missions and firepower for destroying the enemy before they strike. That massive lift fan chokes the internal weapon bays, limiting what the aircraft can carry into the heat of battle. You lose the vital space needed for 2,000-pound heavy anti-ship munitions that are required to sink destroyers. Consequently, you are forced to trade your stealth advantage for ammo by carrying weapons externally on the wings instead. When the F-35B is in cruise flight, that fan is just tons of dead metal dragging you down. It doesn't help you shoot further, it makes you weaker, and it limits your overall combat effectiveness significantly. The British accept that trade-off because they defend the European coast, where ranges are short and manageable. But for the United States Navy, if you put the F-35B on the Ford, you ruin the ship. You have just turned a nuclear fortress designed for ocean dominance into a glorified coastal helicopter pad for Marines. It is like using a massive nuclear reactor just to power a simple toaster in your kitchen at home. And that is when we have to look closely at the harsh reality of the Lightning II family. Look, the F-35A has become the gold standard for air forces globally, replacing older fleets with stealth technology. The F-35B has opened a new era for small fleets and amphibious ships that lack long runways for takeoff. But the F-35C, it is an exclusive anomaly that stands apart from the rest of the fighter family. It is not designed for the masses, and it will never be sold to just any allied nation. It is operated solely by the United States Navy on the strongest supercarriers in the history of mankind. Why is this the case? Because it is the only variant that deletes that damn fan to pack fuel. It is the only variant with wings large enough to dominate the vast distances of the Pacific Ocean theater. But here is the real joke of physics that makes this entire situation so incredibly ironic and frustrating. The Ford was born solely to serve the monopoly of the F-35C and its unique requirements for launch. The F-35C was born solely to operate on the Ford, creating a symbiotic relationship between ship and plane. But right now, they cannot touch each other, remaining separated by a wall of technical and physical incompatibility. Look at the Ford's deck today. It is empty, showing no sign of the F-35C anywhere on board. The world's most modern ship is rejecting the world's most modern weapon, creating a paradox of immense proportions. Why is this happening? Because this plane runs 700 degrees hotter than the ship can handle safely, because it is louder than human survival limits allow, threatening the hearing of everyone on the flight deck. And because it demands things that the engineers who designed this ship in 2005 never even imagined possible. We built a cage in 2005 for a monster from 2025, and now that cage is slowly cracking. We are about to dissect this $13 billion paradox, bolt by bolt, to understand what went wrong here. If you appreciate raw engineering over political headlines, hit subscribe to join the inspection team for this deep dive. Now, how do you fix a physics error on 100,000 tons of steel floating in the middle of the ocean? Welcome to the Synchronization Gap, where the timeline of the ship and the plane do not match at all. We agreed that the F-35C is mandatory for future warfare, and there is absolutely no alternative to its dominance. So why was the Ford, the most modern ship, delivered to the Navy without being ready for its main weapon? Many critics call this poor planning, but I call it the cruelty of material science in a changing world. Look at the shipbuilding process, where every decision is permanent and every mistake is etched in heavy metal. When you lay the keel for a 100,000-ton ship in a dry dock, you make a commitment. When 10-inch thick steel plates are welded together, you cannot hit Ctrl-Z to undo the work you have done. You cannot download a software update to change the diameter of a water pipe or the location of a bulkhead. This is a critical engineering concept called the frozen baseline, which dictates the final physical form of the vessel. Rewind to the year 2005, which was the year the United States Navy locked in the Ford's hull design forever. At that specific moment, engineers had to make life or death decisions about the internal structure of the ship. They had to decide where the wires go, how big the cooling pipes are, and what the generator output is. The problem was that in 2005, the F-35C was just a promise that existed only on digital computer screens. It existed on CAD drawings, but it hadn't flown in the real world to prove its actual physical capabilities. The most critical documents, called interface control documents, governing weight, exhaust temperature, and power requirements, were still totally fluid. The Navy fell into a strategic trap called concurrency, believing they could design both complex systems at the same time. They applied a design-build strategy, constructing the shell of the ship while waiting for the guts to arrive. They built the massive hull while waiting for the plane, the radar, and the catapults to be finished elsewhere. It was a massive industrial gamble that risked billions of taxpayer dollars on a timeline that was far too optimistic. They went all in on the bet that the two puzzle pieces would snap together perfectly at the end. They lost that bet because the construction of the CVN-78 ran much faster than the development of the plane. It was born before the final technical requirements of the F-35C were locked down by the aviation design team. The physical difference of the finished C variant was a shock, because the F-35C isn't just a repackaged Hornet. It is a completely different beast, and we must start by looking at its first violent contact with the deck. The Navy calls it a flareless landing, which sounds gentle, but physically it is actually a controlled industrial crash. Pilots drive a 30-ton aircraft straight into the steel deck without pulling the nose up like older jets do. The massive 2005 hull structure was never prepped for the frequency of this violent surgery on the flight deck. When it stops, the logistical nightmare begins, because its folding wings consume space and force crews to rewrite protocols. But all those physical pressures are nothing compared to the invisible burden it carries, which is massive amounts of data. The F-35C is essentially a flying server wrapped in a stealth shell, thirsting for information before it even launches. The fiber optic infrastructure of the 2005 design simply didn't have the bandwidth to feed this digital monster adequately. To operate the F-35C, the ship is forced back to the shipyard for a massive upgrade called planned incremental availability. However, the problem is the monster we locked inside breathes fire hotter than the hell the cage can withstand. The war between steel and fire begins right here. So welcome to the harshest test, called the thermal module. Do not look at the F-35C as an airplane, because thermodynamically, it is an industrial blowtorch with wings attached. The old Hornet has two engines to split the heat, but the F-35C funnels thrust into a single nozzle. When the pilot kicks in the afterburner, the exhaust temperature spikes to 3,600 degrees Fahrenheit instantly. Recall your basic metallurgy, because steel does not need to melt into liquid to fail under such extreme stress. At the 1,000 degree threshold, steel starts to lose hardness, and at 2,000 degrees, it becomes like clay. With the massive blast of the F-35C, the deck will permanently warp under the 30-ton weight of the aircraft. You cannot launch a jet from a deck that ripples like a potato chip. So the Navy needed solutions. If you use old deflectors, the passive steel side panels will turn into candle wax before the plane leaves. Engineers had to operate on every deflector, threading a vascular system made of special alloy inside the steel panels. They pump cold seawater directly from the ocean into the core of the panels to absorb that rage. But the fire isn't the only thing being destroyed, because the traditional non-skid coating at your feet has surrendered. Facing the thermal shock of the F-35, the chemical epoxy does not just melt, it actually explodes into pieces. The deck surface flakes off in chunks, turning into sharp shrapnel ready to be sucked into the expensive engine. This is the moment we abandon the painting mindset and switch to the armoring mindset to protect the ship. The new solution is twin-wire arc spray, where engineers use high voltage to melt aluminum and ceramic wires. They blast them onto the deck with high-velocity air, creating a mechanical bond at the microscopic level forever. The result is a ceramic metallic skin, the only thing strong enough to stand before the breath of a dragon. But even if the deck doesn't melt under the heat, the pilot is in trouble during the launch sequence. In the first test launches with the electromagnetic system, F-35C pilots reported a terrifying phenomenon known as the bobble. As the shuttle pulled the jet forward, the nose oscillated violently vertically, shaking the pilot uncontrollably in the seat. It wasn't a simple glitch, it was resonance, where the pull matched the natural frequency of the nose gear. The result was that the pilot's head was shaken like a rag doll inside the cockpit during launch. They couldn't read the vital data on their helmet-mounted display during the most critical seconds of the takeoff sequence. In those two most critical seconds of takeoff, they were effectively blind and unable to monitor their instruments. The Navy faced a choice: redesign the landing gear taking 5 years, or find another way to fix it. They chose code, which is the beauty of the electromagnetic catapult compared to the old steam systems used previously. It's not a dumb steam piston that only knows on or off. It is a sophisticated robot launcher. Engineers rewrote the algorithm, commanding the catapult to pull softer for the first few milliseconds to break the rhythm. The nose stopped shaking immediately, proving that a complex physics problem can be solved by smart software engineering. And when the plane leaves the launcher, it leaves a final greeting, a sound frequency beyond biological tolerance. That isn't just noise. That is a death sentence for hearing if you are not wearing proper protection. If unprotected, the crew on the deck won't hear anything ever again after exposure to that massive sound. The F-135 engine noise hits 150 decibels, which is significantly louder than a gunshot blast. At this energy level, sound is no longer an airwave. It becomes a physical weapon attacking the body. Even if you plug your ears, the sound wave travels through bone conduction, going straight into the brain. It destroys hearing permanently by bypassing the ear canal and vibrating the skull directly to damage the nerves. To survive next to this monster, we need a helmet from the future. The advanced HGU-99P flight deck helmet. It doesn't just block noise. It has hear-through technology that changes how the crew communicates on the deck. Microchips inside the helmet filter out the high-frequency screech of the jet engine to protect the ears. However, they allow the frequency of the human voice to pass through, so crew members can still talk. You can stand next to a roaring engine and still hear your teammate whisper instructions into the microphone. Heat-melting steel, vibration causing blindness, and sound-destroying bone are the realities of modern naval aviation warfare. These aren't design flaws. This is the price of power that must be paid for total technological superiority. The Ford is paying that price with every weld, every line of code, and every complex processing chip. After all the thermal destruction and the neck-breaking vibrations, the coldest question is finally asked by everyone. Why does the United States Navy accept spending billions, essentially gutting its newest ship, just to welcome the F-35C? Why don't we keep relying on the workhorse Super Hornet formation that is working just fine for us? The answer isn't in the glamour of new technology, but it effectively lies in the tyranny of distance. Let's go back to the F-35B and remember how the lift fan takes up valuable fuel space inside. The F-35B has a combat radius of about 450 nautical miles when fully loaded for war. The F-35C, by deleting that fan and owning giant wings full of gas, achieves over 600 nautical miles. To a civilian watching at home, that is just a number, but to an admiral, it is life. That 150 miles allows the carrier to park outside the range of enemy ballistic missiles. If you use the F-35B, you are forced to sail a $13 billion ship into the kill zone. So what about the F/A-18 Super Hornet? And why can't it do the job alone in this era? The F-18 is a fantastic aircraft that carries a lot of ordnance, but it is effectively a bomb truck. It isn't stealth, so on the radar of S-400 systems, a fully loaded jet lights up like Christmas. It will be shot down instantly before the pilot even sees the target on his own radar screen. This is where the F-35C steps into the light to save the entire formation from certain destruction. It plays the role of the quarterback, penetrating dense air defense networks like a ghost in the night. It gathers data, redraws the battlefield map in real time, and transmits target coordinates back to the rear. The bomb trucks fly safely in the rear to launch long-range missiles based on that targeting data. Steam is powerful, but it hits the airframe with a violent shock, shredding the fatigue life of jets. This is why the Navy bet the farm on electromagnetic launchers, despite the maintenance nightmares they have faced. Without the F-35C, the USS Gerald R. Ford is just the world's most expensive floating airport using old tech. But with the F-35C, it becomes the physical embodiment of the United States Navy's ultimate doctrine of dominance. It grants America the power to park an invisible air force on the doorstep of any adversary, anywhere. The Ford is the pioneer that accepted sailing with flaws, so its successor doesn't have to suffer pains. Kennedy will have the F-35C from day one, and it will be perfect because of these scars. We use intellect to bend physics to our will, and that is how we conquer the ocean permanently. If you want to see more about naval engineering, please like this video and subscribe to Navy Show immediately.